Hi, everyone. Okay, works. So welcome to this talk. We're going to talk about maps and Google Maps. So I'd like to begin just by a show of hands. Who has worked with maps before on their app? Wow, quite a lot. Almost everyone. And yeah, the rest of you, what are you doing here? Okay. Okay, so my name is Roland. I worked at a company called Amo. It's a French startup, and we do social apps. And one of our flagship app looks like this. So it's based on the map. It's based on the map. And as you can see, everything is moving in all directions. So I'm going to try to replay a second time. Yeah. So we have a bunch of markers. Markers are things that we display on the map. And those markers are animated. Here we have heads of friends that are kind of videos that are clipped. And like it's a bit all over the place, but it's like also what makes this app fun. And so if you're curious about how we do those heads that are cut out, we call them cutouts, there is actually a talk that was made this week by a friend of mine at Amo. It's for iOS, but the concepts are similar than what we do on Android. So please, if you want to see this talk, here is the link to the YouTube video. So the designers at Amo, they design things that are very nice and very well animated, especially on maps. And to make this work, we can't just use the basic APIs from Google Maps. We have to go a bit deeper. And this kind of started me on a journey about maps and to understand what they are, how they work, how they're made, and also where they come from. And so I'd like to begin with a story. And so the story starts with this guy, Oronce Finet. So he's originally Italian, but he lived in France in the 16th century. And Oronce was a very well-regarded scientist at the time. He was a mathematician, cartographer. He did a bunch of stuff. And one night, he was sitting at his desk, like every night, basically. And he didn't expect it, but someone knocked at his door. And it was an envoy. And it was an envoy from the king of the time, Francis I. Now, Francis had just become king recently, and he wanted to assess his kind of power. And to do so, he wanted to know exactly what his kingdom looked like. However, that was not so easy at the time, and they had not such clear ideas of borders and everything. And if you want to be powerful, you need to, well, raise taxes as a king, and for this you need precise maps. And the best map that they had at the time, at the 16th century, was that one. So this is geography from a Greek guy called Ptolemy, just a scientist that invented basically the concepts of geography. He did this map, which is already very precise for the time. It was made a millennia earlier than our protagonists. And we can already recognize a bunch of stuff, like Europe kind of looks like Europe. Well, there is something that where Africa should be, and Asia and everything. And so that was the best map that they had for a very long time, over a millennia. And so back to our protagonist. So he looks at this map, and he tries to understand all the science behind it, how they create coordinates, how they put points on it, and how they basically map the real Earth onto a 2D map. Sorry. And so he walks across France, uses all the data from previously, and tries to improve it, and creates the very first modern map of France. And this map is called Gallier. It's a very big map. It's over a meter wide. Currently, I think it's kept in Switzerland, if I'm not mistaken. Well, and this map is actually pretty precise. We can recognize how France looks like. Fun fact is that the map the kingdom of Francis was not this big. So you can see that it goes all the way to the north of Italy. It goes up north. It goes all the way to Holland. It was not his real kingdom, but he was just preparing in case of future conquests. Like, you never know. We never know if your kingdom is going to get bigger. And well, that map was a total revolution. It changed everything. It was so much more precise. You had cities. Okay, kind of hard to see for you guys at this scale, but you had cities, you had rivers, and it was like very useful. Now, if we look at the most modern revolution about maps, we have Google Maps, 500 years later, and well, it's quite similar. Okay, it's way more precise. We have actual satellite data, but I mean, we didn't improve on that much. Biggest difference is that now we have all this power in our pockets, just on our phones, and we have unlimited access to maps, and this is, well, very useful, as we all know. Today there is a Android SDK that lets us put Google Maps into our apps, and the latest version of this is Android Maps Composable. So from what I got, there is one of the contributors to this repository in the room today, so thank you for contributing to this. And basically, okay, that was pretty fast as a video, but basically this lets us display maps, Google Maps in our app, well, it looks like this. And it works perfectly, but there is a few limitations to it. And those limitations, the designers of my company, they do not really care about them. And so the limitations are mostly that everything is static. Now, don't get me wrong, you can move the map, you can pan around, you can rotate, you can do all these things, but everything that is on the map, the markers, the pins, they don't really move. You can, like the integration with Compose is pretty good, you can take a composable, render it, and put it on the map, but once again, it's not going to be animated, it's not going to be like rendered every frame, and so you basically have a very static map. So I'm just going to show a bit of code about how to achieve just the basic scaffolding for having this map. So it looks like this. So this is a map screen, where we have basically instantiated the composable Google Maps. And this will take care of basically everything that wraps the actual Google Maps, which is in the view system. And then we're going to create a marker and a marker state just to give him some coordinates that long. Now, this works well. And as I said, you can put composable in this, but it's never going to move. And so what we want now is to be able to render composable, but animated, fully rendered composables on the map. So why is this not the case today? I mean, that should be possible, right? So let's take a look at how things are put in retrospect to each other. So let's say this is our app. So it's one process on the phone. And in this app, we have the main thread. Now, the main thread is where Compose lives. And every time we want to render something, well, we have to use the main thread to render it. Now, the rendering of the map, the background of Google Maps, is done in a separate thread. So I'm going to call it the maps rendering thread. So those are two different threads, and they're going to have to communicate with each other to be able for this integration to work. Now, this works fine, and it's in the same process, but it turns out that some operations on this map are not actually done in our process. And there is a separate process, Google Play Services, that will do some operations. And so here you can start to see the issue with this, is that we're going to have communications between two separate processes, which on Android is done via a binder. So the binder is the method of doing inter-process communication. So this has limitations, of course. The throughput is limited, so we can't like animate every frame because of this. Now, this is the new scaffolding that we would ideally have. So same thing, we still have the map screen. we still have the Google Maps. So this is the background of the map. We take in the camera position state. So the concept of camera here is very important. The camera is basically the portion of the map that we render. So it's going to be a target like the center of the screen. It's going to be the rotation, and it's going to be the zoom level. And so we take this, and we feed it into a composable that we want to build, that we're going to call projected. And so projected composable is basically to do, right? And so here is a kind of basic implementation for this. So this is the projected composable. And it's going to be basically a modifier, graphics layer modifier. And so what it does, it first reads the position from the camera state. And this looks a bit weird, and it is weird, definitely. But this allows us to subscribe to changes to this camera position. And so it's going to be re-triggering the drawing phase. So since it's in a graphics layer, it shouldn't recompose. It should only redraw. But still, every frame, we're going to redraw if we move the map, if we rotate, pan, and everything. And then with the camera state, we're going to grab the projection, and we're going to call toScreen location. And what this does, it basically very descriptive. It's going to take a coordinate lat long, and it's going to transform it into the screen position, offset. And we just use this offset to move our composable to the correct location. And well, voila, we basically have it. So this is still Francis, Francis the First on our map. And he's animated. We can tap on it. Yeah, there is a bunch of glow behind him just to make it very clear that this is an actual composable. So we have this kind of overlay on top of everything that tries to follow as best as possible the map underneath. And maybe it's not so clear with the video, but it's not perfect. There is some out of sync issue here. And the reason for this mainly is because of this line. So going back to our projected composable, well, we have this toScreen location, and actually also just the projection. Doing those requires an IPC. So we have to talk to the other process, Google Play Services, to access, to do this calculation, right? And okay, it's just a few, it's a few instructions. We're just gonna do some math operation. It shouldn't be so hard. But if we look a bit into the details of how it works, it means that we have a coordinate. We're going to first parcelize it, because IPCs need stuff that is parcelized. We're going to send it via the IPC binder, and then we're going to unparcel it, do the projection, reparcel it, send it back, unparcel it again, and then finally we have our offset. So there is a bit of a round trip. Now for 1, 2, or maybe 10 markers, this is fine, and it's going to work for your app if you want to just have a few markers on the screen. Well, turns out our designers don't want only 10 markers on the screen, they want 1,000, maybe 10,000 on the screen, and it needs to be performance. Now, what happens if we keep this idea and then that we take 10,000 markers? Well, the profiler is not super happy. So this is the flame graph from an app, just a sample app with the same technique, 1,000 markers on the map, trying to move things around. And well, as expected, the projected composable is taking a lot of time. Almost half the time, half the CPU time is taken by this. And then most of it is the toScreen location call, and the projected, to getting the projection is also an APC. So both of them are really slowing us down. Now the question is, can we do better? If it's just this, we're way too limited. Now, turns out it is possible to do better. But for this, we need to dig into this concept of projection. So let me talk about projection for a bit. Now, what is a projection? Well, in general, it's the concept of taking something from a higher dimensional space into a lower dimensional space. And for in our topic, it's taking something that is 3D, like real Earth, and put it into a 2D a map here. So there are many ways to do a projection. And actually, there is a theorem about this that you cannot have a perfect projection. During my research, I found some very fun projection. I just want to show some of them to you. Can't click anymore. All right, this works. Peter's projection, I guess most of you have seen this one. It's pretty famous because it's like a more accurate representation of the Earth. Basically, this projection is nice because it keeps areas, like the relative sizes of countries and continents is more accurate. So we can see that for once, Greenland is not as big as Africa. So that's nice. We have that one, which is a bit weird, like it's not even in a rectangle. So to achieve this projection, they basically took a cone, put it on top of the Earth that is a sphere, and projected to this cone. And so different one, we have that projection, which really looks like we took a globe and unfolded it and cut it in some spaces. And yeah, this map actually solves the Greenland issue. We have part of it for the US and part of it for Denmark, so much better. We have this map as well, Werner's projection, which is just nice because it's a heart, like just so cute that they did it. Well, this map actually got made. Like it's a real 16th century map that was made by 2 meters by 2 meters of size, and it's. I mean, the thing is huge. It's very precise, except for a weird detail on the map, which is like the lower part. There is a continent that doesn't really exist. It's just a fictional continent that the scientists at the time, they thought that Earth needed to be balanced somehow, and so they just put a continent there just in case if there is something, it's already there. So yeah, it was not super precise, but guess who made this map? Same guy as before. Just after traveling across France, he went ahead and built one of the most precise maps of Earth. And this brings us to the one map that we know so well, Mercator projection. This one is very widely used. And the reason for this is that this map keeps angles. Now, we saw other maps that keep other things like areas, but this one keeps angles. And this matters a lot for ships, because ships, whenever they want to go to a direction, they take their compass, they try to align the angles, and then they know in which direction they're going to go. So Mercator's projection is not so precise for areas, but it's very precise for angles. Now, the version we use today is not exactly Mercator projection. Some people call it a pseudo-Mercator, but usually we call it a Web Mercator. And the difference between the two is not so great, is not so big, sorry. Mostly that Web Mercator is a bit less accurate. It uses a different approximation of Earth. It got popularized by Google Maps, and is now a very widely used standard in the programming industry. Okay, so those were pretty cool projections, but let's see exactly what the process is to turn Earth into pixels on our screen. So first step is to take Earth and to approximate it. So there are many ways to approximate it. There are standards, of course, and the approximation that we have with Web Mercator is a sphere, like plain old sphere. It's not the most precise, but it's the simplest, which is good. And then we take this sphere, and every point of this sphere we're going to project into 2D. So here it looks like this, and then we're going to do some linear transformation into the screen. Simple enough, right? So let's dig a bit more into each step. So if we look at the Mercator's projection, the main idea is that we're going to do projection on a cylinder. So we have a fictional source of light inside of this sphere, And every point that touches the sphere is going to be projected onto the cylinder. And so we're going to have a cylinder that looks like this. And when we unfold it, well, we have the full map. Now, I don't really know why this map is cut at 70 degrees. But the actual Web Mercator is cut at 85-ish. They just wanted to make this thing a square, because we do really love squares that make things very simple. OK, so if we put this in code, it looks like this. It's just like a few lines. Like, it's the simplest thing ever, because, well, we did all those approximations. Input is to take a coordinate, lat long, and then we just calculate an offset from this lat long, right? So, well, a couple of instructions. I'm not really going to dig deep into the math, but it's like trigonometry. It's super easy to find this online, actually. Right, and so the other part that we discussed was the linear transformation. So I'm going to show this now. So if we have a linear transformation, what do we think about? We think about matrices, of course, because this is the way to do linear transformation. And so this is the matrix that we use in our case. Once again, just a couple of lines of code. We need to translate to find ourselves in the center of the screen. Once we're in the center, we actually do the rotations. Then we translate back to the correct position on the map. And then we just invert the y-axis, because no one can agree on what's y is, if y is up or down. But well, you just need to do this. And so this builds a matrix. And using this matrix, we're going to be able to move our dots into and to basically have points on the screen. So if we put everything together, it looks just like this. Once again, we take a lat long coordinate, we project it using Web Mercator, and then we map it with the matrix. Now, there is just this tiny little function that I did not explain, but we'll go to that later. But all in all, that's just the whole process, right? So we take this function, we put it back into our projected composable, and voila. And we don't have the screen anymore. It's back, perfect. And voila, we have our projected composable with no IPC, so much faster. And we might have solved the issue. Can I click? All right, so this is same again. So we still have François Premier, but Francis, sorry, the first. It's half English, half French. But this time he has some other monarchs. Oh yeah, and rotation works, of course. Okay, I wanted to make the video loop, but it just doesn't work on Google Sites. Okay. All right, so we did see a lot of stuff, so maybe now is a good time to recap. So how well did we do on our task? So we wanted to show real composables on the map, and well, this is true. We have actual real composable on the map. We have very few IPCs, and we handle zoom and rotation. Now, the issues are, there are some drawbacks. Like, we don't handle tilt. Maybe there is a way with matrices, but I couldn't find it. The biggest issue is that the sync is not guaranteed. So this means that if, for any reason, we block the main thread a bit too long and that we miss a frame, well, the underlying rendering of the map is going to continue, keep moving, but we're not going to follow on with our overlay. And so this is going to be a bit out of sync. In practice, it's kind of hard to see, so most of the time this is fine. And then there is a bit of issue with gestures and map. As you can imagine, if you're starting a gesture from the map and then moving to a composable, or vice versa, the system is not going to like it so much, and so there are ways to make it work, but like out of the box, it's not going to work perfectly in some cases. But anyways, if we take a look at our flame graph, well, we're not taking half the CPU anymore, so this is much more efficient. OK, so we have this system. We did a bit of math. We did a lot of research. What can we do with this? Well, this is sticky markers. So yeah, the idea is that when a marker is out of the screen, we're going to just keep it on the screen. We have arrows, because we know both the starting position and the actual position, so we can point to the correct direction. All right. And the code to achieve this is very small, once again. So we just have our transformation in our graphics layer, and this time we just coerce it into the screen size. So, well, very handy for this. This is how we animate movements. So the monarchs are sending each other letters. Short video. OK. And yeah, once again, this is not so much code. We just have to convert from lat long into animation vector and use the normal Compose APIs. Maybe one last. This is the 3D line effect. So just using rotation, we can do some other math, basically to compute how the line would behave if it was 3D. This is just like a cool effect that is kind of cheap to achieve. Here's the code for this. No real need to dig into the details, but basically we have those 2 points, and we're going to try to do a Bezier curve between those 2 points, and the Bezier curve is going to change based on the rotation, right? So, OK, there are many, many possibilities. At my company, we build a whole framework around this idea. We build things around marker collisions, because since we know the exact positions of each marker, we can detect collisions and try to shrink some of them to show only the important ones. We have concept of implicit focus, which is trying to guess what the user's intent is, because whatever's in the middle of the screen is probably what they're looking at. And so we can make it bigger or more easier to interact with. So yeah, there are a bunch of ideas. But all in all, everything in here is all about points. And by points, I mean markers. But we'd like to take it one step further, and this is to actually show zones, like highlight areas on our map. And to do this, we need to talk about the tile system. Now, the tile system is a step that I didn't talk about in our previous slide. So once again, this is the way to take a point on Earth and to put it on our screen. And we just add one more step, which doesn't show. Does it? No. OK. One more step, and it's to convert into pixels. And to convert into pixels, we need to use this system. So how does it work? The tile system is linked to zoom levels. So at zoom level 0, we're going to put the whole of the map into one tile. So we have a single tile with the fixed size, and we put everything in it. It's just 256 pixels of size by side. And then on each new zoom level, we're going to subdivide to have more tiles. So this is zoom level 1, zoom level 2, and zoom level 3, and it keeps on going. And as you can see, the more we zoom in, the more resolution we have. And so the correct way to think about this is as a pyramid. What happens is that every time we increase the zoom by 1, we're going to multiply the scale by 2. So this is a exponential, and it allows us to quickly represent very small details, like very zoomed in, and also like being very zoomed out without having to deal with big numbers. And so the correct way to think about this, if I can do it, all right, is that the map is actually expanding on the screen. And so the screen size, of course, doesn't move, but it's the map behind it that scales up and down when we zoom in and out. now that we know this, we can just create the last few methods. So this is how we transform a zoom level to a scale. It's just like take 2 and do power of 2 to the power of the zoom. And then we have, so this is how do we compute scale. And then we have a bit more linear transformation just to move into the world and to be in the correct area. But this is like, it looks like this, basically. And so we have it all. We have the whole system, we have the whole methods. We don't need to do IPCs anymore. And we even now know how to render tiles. And this is a video on how to render some tiles. So each country is highlighted. It's a different area. And what happens here is that Google Maps is asking for a tile, so X, Y coordinates and Z coordinates, which is zoom. And we're going to feed Google Maps those tiles. Now, something's pretty clear from the video is that it's blinking quite a bit, and sometimes it loads slowly. So part of the reason is that the code that does it is pretty inefficient, but that's almost on purpose, just to show the issue. But yeah, I mean, it's not like perfect user experience. So anyways, this is the code that does it. Here is how we create a tile. So we start by creating a bitmap of the correct size. And then we prepare the data. So it's going to take the path of the different countries, scaled up with the correct values. And we're going to use that path and this data to draw into our bitmap. And then we're going to return this bitmap, give it to Google Maps, and it's going to be able to render it on the screen. Now here I don't know if it was very clear on the video, but there was a bit of gradients going on. And to achieve this, there is a shader behind that just draws a Perlin noise gradient behind to make it a bit more interesting, right? So this is using the basic, like the normal API for tiles. And it has some good sides, like guaranteed sync, meaning that the areas that we highlight are always going to be perfectly in sync with the map underneath. It's simple to use. That's also a good point. But the main issue is that we're going to do a lot of decoding and encoding of images because Google Maps expects us to give PNGs or WebPs, and we have bitmaps, so we have to encode them. And then on the other side, there's going to be redecoded again. And so this can be a bit cumbersome. And then there is the blinking issue. And that's kind of linked to how Google Maps handles cache. And so if we zoom in and then back out again, it's not going to remember the tiles that we used to use. And so it's going to be redrawn completely from scratch every time. And so, yeah, basically the cache is also limited. So can we solve it? Well, we have all the tools. And we can create a compose-only tile overlay, which will basically bypass the whole API. And if we implement it correctly, it's going to solve those issues. So that's pretty much it for me. And I'm just going to leave the last word to Oronce. So let's make some awesome maps. And yeah, thank you very much.